where would you like to start?
Number 4.
Number 4 is a great one. That's the pool, right?
Yep.
Okay. All right. Okay, so for number 4, it says filling a pool. A swimming pool is 50 meters long by 20 meters wide. Its depth decreases linearly along the length from 3 meters to 1 meter. It is initially empty and is filling at a rate of 1 cubic meter per minute. And we want to know how fast is the water level rising 250 minutes after the filling begins, and how long it will take to fill the pool. So let's start with drawing our little picture of our wonderful swimming pool.
Is number 4?
Yeah, number 4. So we have this swimming pool that's going on like this. And then we got our third dimension, of course, going out in this direction. I'm going to focus only on that 2-dimensional thing to look at to help us figure it out, visualizing it. But that's our pool going on. And we were given some information. What was given to us? What do we know about this pool?
We know the length and width of the pool. We know, and we know how deep it is. Deep it is.
Okay, so we know the length is 50, width is 20, it's 1 meter here, and it's 3 meters here. Okay, anything else we know about? It is filling at a rate of 1 cubic meter per minute. So what would be my notation for 1 cubic meter per minute in calculus notation? What would that be? The pool is filling at a rate of 1 cubic meter per minute. Units are a hint. What is measured in cubic meters? Volume. So this is the derivative of volume, the rate of volume over minutes, over time. So it's dV dt. How fast is the water level rising? 125 minutes after it's beginning to fill. So I need to identify some variables on here for me to work with so that I can work with this. So I probably shouldn't have used blue. I'm putting this to purple. So my water can be blue. I don't want purple water. Okay. And so let's say I'm filling this pool, and at one point in time, let's say it's up to here. We got a water level at this height. I'm only going to shade in this 1 dimension, this 2 dimension here. I'm going to do over on this side, but you understand it is filling up on that side as it goes. And so we want to figure out the water height, the rate in which the water height is changing. So I'm going to let W represent this water height. So let's let W equal the height of the water in meters at any given height. So that's going to be our height of our water in the pool. And we'll let X here represent, because as this is filling up, this distance here is also changing. That's a rate, that's something that's changing. As water fills up, that length is getting longer and longer. So we'll let X equal the surface length of the water. And that's length, so that's also in meters. That's being measured. Yep.
I was just gonna say I like these questions a little better because they actually make sense to me. Because of like application.
You can see the application of it, of why we've been learning this implicit differentiation. All right, that's good to know. All right, so now that I know some of those notations, what would be the calculus notation I could do to represent how fast the water level is rising? That's what we need to find, how fast the water level is rising. D what?
Or DW, sorry, I have it.
Okay, so dW over dt. That's what we're trying to figure out. We're trying to figure out water. The water level height is changing. And we want to figure it out after 25 minutes of filling the pool. So after T equals 250, sorry, I said 25. 250 minutes. Okay, so I have a rate that I know and a rate I need to figure out. So I have volume and I have this W. So my goal is I need to figure out an equation that involves those two variables, W and V. So what is an equation that can involve that W and that V? You don't have to come up with the equation itself, just in general. What would we be looking for to figure out an equation that would make the what? I didn't hear you. Uh-huh.
Finding the rate at which the legs change.
No, we don't want to add a new rate, because we have a rate of change of volume and a rate of change of the W, the height of the water. So we don't want to add another one because we don't know that. We only know one related rate, so I want to compare one rate you know and one rate you don't know. So I want to get an equation. Now, to get rate of change, we differentiate. So I got to go a step above. I got to get the equation first that I want to differentiate. So I don't want any rate of change. I want an equation that involves V and W. So it involves volume and the W. So I need volume of the water. Does that make sense? Because W is measuring a measurement of the water. So I need to figure out an equation for the volume of the water. But I run into a problem on figuring out this equation for the volume of the water. I have drawn the water down here where it's just a triangle prism. But do I know it's down here, or could it be up here where it might be a trapezoidal prism? Okay. How can I figure out where does it make sense for it to be down here? Or does it make sense for it to be up here? How can I figure that out? Okay, when do we know when the pieces break up?
Once it reaches 2 meters, once W is 2 meters.
Okay, but how do we know if W is unknown? How do we know W is, where do we know which equation to work with?
Well, the rate of change is W can be.
Huh?
We can know how tall the level of the water is. We just don't know how fast that is changing. That's what
Well, we don't know, but how do we figure out how tall the water is? We don't know that right now. How can I figure that out? I mean, you can find it, but we haven't done that yet. All right. Imagine I have, let's break this up to 2 pieces. Okay. So below, if the water level of X here, that water level is below the green line, I'm going to have a trapezoidal, a triangular prism. If it goes above that green line, I'm going to have a trapezoidal. So that's sort of like what you're looking at piecewise. So we're doing that kind of piecewise there. We're going to look and figure out which one. So maybe I can look at how much volume I would need to fill in this green triangular prism. If it went to that, can I figure out that volume? Because here, how do you find the volume of the triangular prism? And that's the first question asked. Volume of the face, which is a triangle. So how do you find, the area of the face, how do you find the area of the triangle? 1/2. Okay, and what's this length here?
X.
It's not X. green. What is it for when it's green? 50. You're up to 50. You throw the whole length of the pool. And what was the Vita's height here? 2. Okay. So what's 50 times 1/2 times 2? Okay. Now that's area of the surface, but then we need one more dimension. Sorry. We got to multiply by how many of those triangles they go. That goes at 20 meter deep. So multiply by 20. So we get 50 times 20, which is 1,000 cubic meters. So if my volume is up to 1,000 cubic meters, then I would have to be above that green line. If it's below 1,000 cubic meters, it's going to be below that green line. Now, I did give volume, but I did have that volume, that the rate of change of the volume is 1 cubic meter per minute. So how long would it take the pool to get to 1,000 meters? 1,000 minutes. But I'm looking at only 250 minutes. So we know we have to, I drew it correct, I'm below that green line. So that's just some reason that you have to go through. You can't assume it. You have to kind of figure out that we're below it. Okay, so that's good. Makes life easier. We're just looking at the triangle prism here. So now I'm going to look at the blue triangle prism. So I'm going to look at this. That's filled in with water here. Covered up my W. So what would be my volume formula for the blue one now? Volume is equal to 1/2 W times X times by 20. Simplifying that down a little bit, that gives me 10 WX. But I have a problem. I want it V related to W. I have this extra variable X. So I need to get rid of that. So I got to ask myself, is there any way I can rewrite X in terms of W? I think I didn't quite hear that. What was that?
What's this surface length of the water?
X, yeah, surface X is the surface length of the water. How did you get that?
Well, it's 50 divided by 2.
Why is it 50 divided by 2? Well, how do you know it's halfway? We don't know it's halfway. Yeah, they change, but we don't know the rate in which it changes. We don't know which rate they're changing. Okay, think about it like this. Here we have one triangle. That's W by X. And then here we have another triangle that is 50 by 2. Ah, they are similar triangles. How do we know they're similar triangles? We have 2 right angles and they share this angle. So we have angle similarity. So we got to use those similar triangles here to help us kind of relate this. So in the blue triangle, in the water triangle, I can say that W is to X, as in the green triangle, what would that proportion be? Okay, W first, so I have to do 2, is to 50. Since W is on top, the 2 has to be on top on the other triangle, the corresponding sides. So now I can solve this for X. So cross multiply, I get 50 W equals 2X. And then X is equal to, and then that's where you got the 25W. I just need you to explain it. Okay, so that's where we get that W is equal to 20, X is equal to 25W. So I would go over to this equation. Notice I haven't done any calculus yet. This is all algebra and geometry. And I'm going to replace X with 25W. So V is now equal to,
V is equal to 250 W squared.
very good, 200. No, that's not writing very well. Let's try that again. 250 W squared. Now I have the variable I want to find the rate of change to, relate it to the variable of the rate of change I know. Now I'm ready to differentiate. So what is the derivative of V?
It's 500 W.
No, what's the derivative? What is the, let's differentiate this. You're jumping ahead again, that should work. What's the derivative of V? Okay, that's dV over dt. I don't know. It's very frustrating. Somehow it doesn't track that I've moved it. dV over dt equals, what's the derivative of 250 W squared?
500 W times W over dt.
500 W times dW over dt. All right, so let's substitute in anything that we know. Well, we know dV dt. So that's 1. I need to find dW dt. That's my unknown that I want to find, so I'm going to keep that as a variable. So I got this W I need to figure out. So I need to figure out what W is. Is there any way I can figure out W?
Take X from that 250. I don't know. Try to separate it. But we don't know X.
But do I have enough data that I can figure out X?
Yes.
Or
So
W?
we have to find X to find W to find. What is this?
Well, we can only, okay, think of this. We have this volume formula here, right?
Yes, ma'am.
Volume is equal to 250 W squared. After our time, we haven't used this time. Our time is 250 minutes. So what would be our volume of the water after 250 minutes? What should that volume of the water be?
250 meters cubed.
Oh, because it's filling up as 1 minute, 1 meter per cube per minute. So that means after 250 minutes, my volume is 250 cubic meters. So I have 250 is equal to 250 W squared. So 1 is equal to W squared, W is equal to plus or minus 1, but which one only makes sense in this problem? The plus, because that's the water height. So it doesn't make sense that the water would be negative. So W is 1. So that means I can plug in now 1 in place of W. So that gives us 1 divided by 500 is equal to dW dt. So let's figure out our units of measurement. What is W being measured in? Meters. Divided by, what is T being measured in? Minutes. There's your answer for the first part of the question, part A. So my sentence, we're asked how fast is the water level rising 250 minutes after it's being filled. My answer would be 250 minutes after the water is starting to fill, the water level is rising at a rate of 1/500 meters per minute. So that could be my sentence that goes with that. How long will it take to fill the pool? Question B. How would I figure out how long would it take to fill the pool? Okay, so we can find the volume. Well, first we gotta find volume, then we can talk about time. But well, let's yeah, I'll do what you said. So time to fill the triangular part plus the time to fill the rectangular part, the top part. Some people said that's the bottom part and the top part. Okay, we can't do it that way. But how can I figure out the time it takes to fill? Find the volume. So I actually need to find the volume of the bottom part. That's the triangle part. And add the volume of the top part, which is the rectangular part. Okay, so how do I find the volume of the top?
Top is just 1 times 50. Well, the top rectangular section, because since it's a rectangle, if you're finding the area of the cross section, multiply that by 20 to find the total volume.
Yes, so it's going to be that 50 times 1, which is that area of that rectangle, times by 20. So that volume of that top is going to be 50 times that 20 times that 1, which is just simply, what was that? 50 times 20? 1,000. I kept hearing 4,000. It's 1,000. Okay. All right, so how do I figure out the volume of the bottom?
1/2 base times height times 20.
Yes, which we did earlier. That's the green triangle that we did earlier to check from where it changed over. So that's that 1/2 50 times 2 times 20. Which we already figured out to be 1,000. So our volume is 2,000 cubic meters. But that wasn't the question asked. The question was asked, how long would it take to fill the pool?
2,000.
Because the rate in which it's being filled is 1 cubic meter per minute. And so that would just be 2,000 minutes to fill. So it'd take us 2,000 minutes to fill the entire pool. Okay, now questions, anything that you're not sure about that one? Okay, any other questions, any other problems?
Number 7 was just kind of fun.
All right,
It was an interesting.
number 7. Okay, that's the women walking, okay? So we have a light post that's 20 meters or 20 feet. I think it was feet, yeah, 20 feet tall. And we have this woman walking toward it who is 5 feet tall.
Oh, you're not going to give her a little stick out?
I know, I'm being very picky on my drawing here. And we want to figure out, we're talking about here is the shadow, okay? That's going from that light. Okay, so let's see. I'm going to call this S for the length of the shadow. So I'm going to let S equal the length in feet of the woman's shadow. Okay. I'm going to let, because she's walking closer and closer to the lamppost, that's going to change. So I'm going to call that D. Then we'll let D equal the distance she is from the light post
Should that be a different variable? Because
in feet.
the rate of change of D is going to be dD over dt.
You can have DD over DD.
Gross.
It just looks weird, but yeah, you can do that. If you don't like that variable, use another. Yeah. You can choose, that's the reason why you define your variables. You can choose whichever letter you like. All right. So let's see what they asked us to find for, what information was given to us. So a 5-foot-tall woman walks at 8 feet per second and toward the street light. Okay, so 8 feet per second toward the light post. What would be our calculus notation for that? You got it. So we know that the rate and change of that distance that she is from the light post is equal to 8 feet per second. And she's getting closer and closer, right? So that should be negative. Negative 8 feet per second. Our distance is decreasing. Okay. Now let's look at what we need to figure out. What is the rate of change of the length of her shadow when she is 15 feet from the street lamp? So what's our calculus notation for the rate of change of the length of her shadow? All right, so we want to find ds over dt. That's our unknown. And we want to do that when she is 15 meters from the street light. So what would that notation be? D is equal to 15. So when D is equal to 15. Okay, so it says I need to relate D and S. The rate of change I know, the rate of change I don't know. So I need to come up with an equation that relates D and S.
Well, I mean, you can, using what we have so far, we can solve for several variables. I mean, we know that S is, we can find out that S is equal to 5.
No, we can't do that yet. No, we can't.
Why not? Triangles are proportional.
We, because we can't use this D as 15.
Okay, well,
Because you don't use that to IQ differentiate. We can't use that yet. To set up your equation, we want the variable S. We want S, if we need the variable S, we need the variable D. So we have to get an equation that has D and S in it. Or we won't be able to get those rates to compare. So what's some equation that we can relate? Think, just like we did in what part of the other problem. Think similar triangles. I've drawn 2 triangles on here. Think similar triangles. I have this big, long, big triangle, and then I have this little triangle. So think about this big triangle here. Is it similar to this triangle?
both have right angle and they'll share the angle from the hypotenuse.
So we have angle similarity. So why don't we try setting this up with proportions then? And this is a common trick you want to use with these triangles. With these shaped ones, you're going to do similar triangles quite a bit, or similar objects. So what would be our proportion that we could set up with that? Using the red triangle and the purple triangle.
The length of S, or just to
Set up the proportion, just set up the proportion. Comparing those 2 similar triangles. What's the proportion of one triangle related to the other triangle? So the small triangle, we can look at S is to 5. As in the big triangle, what would be our proportion? D plus S is to 20. So you can set up. So you've related the corresponding sides of the small triangle to the corresponding sides of the big triangle. Notice this equation only has S's and D's. That's good. That's what I wanted because I need to find the derivative with S and derivative of D. Cross multiply. Simplify. And I get D. Well, I probably should solve for S. I get S is equal to what? 1/3D. That doesn't look like a 3. I said a 3, but I wrote an S. 1/3D. Okay. Solving for that, dividing each side by 15. So I've now found an equation that relates only the two that I need. The D variable that I have a rate of change for, and the S variable that I want the rate of change for. So now my next step is to differentiate. So let's differentiate the left-hand side. What's the derivative of the left-hand side? ds over dt equals what's the derivative of the right-hand side? 1/3 dd over dt. All right, let's plug in what information that we know. Well, we know that dd over dt is -8. So that's -8/3. All right, S. What's the unit of measurement for this side, this S, the length of the
5.
shadow? That's what?
5.
5?
S is equal to 5.
No, what is the unit of measurement for that
Oh,
length? Feet. So that's our top unit, divided by, what's our unit of measurement for time?
second.
Seconds. So we know when the woman is 15 feet from the street lamp, the length of her shadow is decreasing at a rate of 8/3 feet per second. And we figure that out. Now, B asks us to find at what rate is the tip of her shadow moving. So I'm going to add another variable here. I'm going to let big T equal the length of the tip of her shadow, the tip of the shadow. So that's going to be that total distance there. So big T is equal to the distance, the tip of the shadow is from the light post. And that, of course, still is in feet. I use big T. Because I could use little t because T, that's time. We've already have that variable. So I did choose another variable. I did T for tip. But you could have chose whichever variable you want. So I can go back to this proportion here and just rewrite that as S is to 5, as T is to 20. You agree with that? That's all I've done right there. I haven't changed anything. So that gives us 20S is equal to 5T. And what are we trying to find? We're trying to find at what rate is the tip of her shadow changing. So what are we looking for this time?
dt over dt.
So we're looking for dt, big T over dt. This is what we're looking at for this time. So I probably need to solve for t. So that gives us 4s. T is equal to 4s. So I can differentiate that, just like we've been doing. And derivative of the left-hand side would be times
cs over dt.
equals.
dt over dt.
And we know ds dt because we figured it out in part 1. And so what would that give us?
32 characters.
And so T, big T, what's our unit of measurement for it? feet. And what's our unit measurement for little t? Seconds. So, my sentence. The tip of her shadow is decreasing at a rate of 32 1/3 feet per second. So that's the simplest way I have it. There's other ways, but that's the simplest way that I found that you could do those too. The simplest way I see. Any others? You sure that was the only two that y'all had questions over?
No, I have 100.
I know, I gave it more. 8. The sand pile. Okay. So, a sand falls from an overhead bin and accumulates in a conical pile with a radius that is always 3 times its height. Suppose the height of the pile increases at a rate of 2 centimeters per second. When the pile is 12 centimeters high, at what rate is the sand leaving the bin at that instant? Okay, so we have this kind of, and the sand is falling in right here. And it's kind of conical shape. And again, since I do so terrible on 3Ds, I want to do it flat to work with a little bit. But notice that that is a 3D shape. And so this is my radius and this is my height that I know. Those are basic variables, so I don't have to define those. Those are given variables traditionally used. If you want to define them, you can. But I have a relationship between R and H. What was our relationship that we had? Okay, so the radius is 3 times its height. So we know that R is equal to 3 times H. That might come in handy. We were given that the height of the pile is increasing at a rate of 2 centimeters per second. So 2 centimeters per second is equal to, what's our calculus notation for that? dH over dt. And we want to figure out at what rate is the sand leaving the bin at that instant. So what would be the calculus notation we got to figure out for that rate in which the sand is leaving the bin?
Well, the way you can find the rate at which the sand is leaving the bin is how quickly the volume of the cone is changing.
Exactly. So you have to figure out that that rate in which it's leaving the bin is the volume that is changing. So it's the rate of change of volume. So it wasn't worded where it's very obvious that time, but you do have to kind of figure out what's going on. Well, it's leaving the bin, it's filling up that pile, so it's changing the volume of the pile. So it's corresponding to the dV dt. And we want to do that when the pile is 12 centimeters high. So when H equals 12 is what we're looking for that at. Okay, so the variable I know is the rate of change I know relates to the H variable. The rate of change I want to figure out is the volume. So that tells me I need to figure out the volume of this shape. How do you find, what's our formula for volume of a cone?
1/3 pi r squared.
Okay, volume of a cone is 1/3 pi r squared h.
But we want to substitute in 3h.
But again, we only want variables h and variable v. So we need to replace the r variable with 3h before we differentiate. So let's simplify that now. So that gives us 1/3 pi times, well, that's 9h cubed. That's 9h squared times h, give us 9h cubed. And what's 1/3 of 9? 3. So this is just 3 pi h cubed. So That's a little bit easier equation to actually differentiate. So now I have an equation that's relating my v variable to my h variable, which was the variable I knew the derivative to, and is the variable I'm looking to find the derivative to. So that means I'm ready to differentiate. So what's the derivative of the left-hand side?
dv over dt.
And the derivative of the right-hand side?
9 pi h squared times dh over dt.
9 pi h squared times dh over dt. 3 pi is just a constant, so we treat that just using the power rule there.
We can substitute that h is equal to 12 with dh over dt.
Ah, so let's substitute in what we know. Let me do it over here so we can see it a little better. Oh, that's an H. Okay, so again, I know dHdt is 2. I know H is 12. I want to figure out dV dt, so that should be my only variable. And it is. So I have all the information I need. It's just some punching into my calculator. So it's 12 squared is 144. 144 times that 18 gives us
2,592.
2,592 pi. And that's dV over dt. V is measured in what units? What's V's unit of measurement?
Centimeters.
No,
Centimeters cubed per second.
cubic centimeters, yeah. So centimeters cubed, and time is being measured in
Second.
seconds. So the rate and change, the dV dt is 2,592 pi cubic centimeters per second. To answer the question, at what rate is the sand leaving the bin at that instant? At the instant where the height of the pile is 12 centimeters long, the sand is leaving the bin at a rate of 2,592 pi cubic centimeters per second. That could be your sentence. Okay, any others that you want to see worked out?
No,
Any?
9.
9? Okay. The fishing rod one. Okay. The angler hooks a trout and reels it in the line at 4 inches per second. Assume the tip of the fishing rod is 12 feet above the water and directly above the angler. And the fish is pulled horizontally directly toward the angler. See the picture. Find the horizontal speed of the fish when it is 20 feet from the angler. Okay, so all right, I'm going to let L here equal the length of the line. So I'm going to let L equal the length of the fishing line. Yes. And no, I think it's feet.
No, what difference is? That's what we'll find.
Yeah, in inches. Okay. Okay, so length of that line in inches. Do we need to go to inches or we need to go feet at the end? Everything else is in feet. I'm going to go to feet. Since everything else is in feet, I want to do feet. We'll just make that one. No. It might be easier for you to convert one dimensions into inches than the rate into feet. Yeah. Sorry. It'll be easier for y'all. We'll do inches. That'll be easier for you to convert. Okay. So we're looking at the length of the fishing line in inches. And then we'll let H represent the horizontal distance the fish is, because our fish is over here from the angler. So let H equal. And we'll convert that into inches. So it can be in the same unit. Okay. And assume the tip of the fishing rod is 12 feet above the water and directly above the angler. So we know this is a constant. It doesn't change. That stays 12. But that's 12 feet. So what would that be in inches? What was that? 144 inches. So if we go to all the inches, that would be up to 144 inches. So let's look at the rate that they gave us. The angular hook of the trout is reeling in his line at 4 inches per second. So that 4 inches per second, what does that relate? What is our calculus notation for that?
That would be DL over DT.
That's the line. That's the rate in which the line is changing. Okay, should that be a positive or a negative? It should be negative because that line, he's reeling it in, so it's decreasing. All right, and then what are we trying to figure out? Find the horizontal speed of the fish when it's 12 feet from the angler.
DH.
So we're trying to find DH over DT. And that is when H is, when the horizontal speed, when 12 feet from the angler, so that is H. So when H is 20 feet, but 20 feet is how many inches?
That's 200. Or wait, no.
Yeah, that's 240.
Okay.
I was just checking. 240 inches. Okay. All righty. So now everything's in inches. So I need an equation that's going to relate L and H, the diagram theorem. So we got 144 squared plus H squared equals L squared. Okay.
Well, since we're trying to directly relate H and L, so if we derive this,
So let's differentiate that. What's the derivative of 144 squared?
0.
That's 0. That's the reason I didn't bother figuring out what 144 squared was. And derivative of H squared?
2H DH over DT.
Equals?
2L, the DL over DT.
And I'm going to figure out DH, so let's go ahead and get DH dt by itself. So divided by 2, so that's 2 just cancel it, that's L over H, DL dt. All right, let's plug in what we know and see if we have anything else we got to figure out in this problem. So I want to find DH dt. I was given that DL dt was -4. And I was given that H is 240. Uh-oh. I have the extra variable L.
We just solve for it using the Pythagorean.
So we just go back to that Pythagorean theorem. Now we can solve for it when H is 240. I don't remember what that is, so let's do it really fast.
When you put DH over DT, what happens with the 2?
You divide it both sides by 2.
Oh, there's a
D
two.
side by divided by
Oh, there's
2.
a 2 right
2
there.
divided by 2.
Okay.
And so that became 1. Okay, so I got L squared is equal to 78336. Okay, they went to feet, I think, at the end.
I went inches for the very last time.
Oh, they went to inches at the end. They're not, I don't think that's right. Well, we'll see. We'll see if that's right. Okay, and so L is the square root of this. I'm not even gonna bother simplifying it down at this point. I'm just gonna plug that in. So I'm gonna take that answer, square root it, divide it by 240, times it by -4.
Should be back to 4.
Yes. Okay. All right, so H, what's our unit measurement for H? Inches, and our unit measurement for T? Seconds. So that's how I'll figure out my unit measurement for my answer. Then converting that into a sentence, we were asked to find the horizontal speed. So the distance between the horizontal speed of the fish is decreasing at a rate of 4.66 inches per second. Now you notice that in the answer key, they did not put the negative, and that's because they were looking at the speed, not the velocity. So direction was not important. So that's the reason why you see in the answer key that the negative disappeared. So you could just say that the horizontal speed is 4.66 inches per second. The speed we are absolute value of velocity. All right, so that's enough for that. We have a test coming up on Monday. Initially, what was the topic for our what's our topic for our test going to be over?
Linear approximation, mean value theorem, implicit differentiation, related rates.
Okay, so implicit differentiation, related rates, and then that videos that you watched about the mean value theorem and the linear approximation. Because I noticed people were having problems with this related rate, I decided to spend another day on related rates. As you can see that we spent this much of class just going over these problems. I have a second related rate worksheet for you to work on. I want you to do some extra practice with this. So your test has been changed. That linear approximation and the mean value theorem will be moved to the next quiz. So the only thing that will be on Monday's test quiz will be the topics related rates and the topic implicit differentiation. On Thursday, we will talk about your videos. So if you need to rewatch them prior to Thursday, you might want to rewatch them, remember. But for the rest of the class, go to Canvas and you'll see a related worksheet number 2. I made it very, very long, but I only want you to work the odd problems, but I went ahead and gave you the even in case you want to go home and practice extra before Monday's test if you want some extra related rate problems to work out. So I went ahead and gave you the full worksheet. The answers again are at the very bottom. I haven't checked them, but I assume they are correct. So you have that. So you can spend the rest of the class working on that related rates. Ask me any questions you have. I'll help you out. This is usually a very complex concept for some.